Let's discuss question number 50 and 51. This is from common data question. So question number 50 and question number 51. Okay, this is one of the common data question from test 1. Okay, and the question is from heat transfer, basically lumped analysis and heat transfer. Okay, so let's first do what is asked. Let's first see. A person is found dead at 5 p.m. in a room. So at 5 p.m. you observe that a person is dead. Okay, the room temperature at this point, the room temperature is 20 degrees Celsius. So I'm just calling that as T infinity. And the body temperature at this point of time, the body temperature is 25 degrees Celsius. So let me write T1 or T2, whatever. Now this is what when you observe, when you just open the room, or I mean somebody has observed that these are the conditions at 5 p.m. The person would have died at some time below, right? Somewhere below, before he would have dead. Actual death would have occurred that time. Okay, okay. And now, because when a person dies, I mean, when a person is alive, actually, so the temperature is just normal body temperature, which is 37 degrees Celsius. So at the time of death, you would expect the temperature to be just at the time of death, the body temperature to be 37 degrees Celsius. But now, when he dies, all this heat transfer, I mean, all this metabolism, every activity that is going on inside the body stops. So now it's basically just a normal body at 37 degrees Celsius. No activity, nothing is going on inside, no heat generation, nothing. Okay, so now it can lose heat because just it's imagine just like an egg, just an egg or any body which is hot body 37 degrees Celsius and no other thing is happening, it's just placed like that, so it will lose heat because outside temperature is 20 degrees Celsius. It will lose heat, and from 37 to it has come down to 25 degrees, it has lost heat and it has come down to 25 degrees Celsius. Now what you observe is that this is the condition at 5 p.m. Okay, and you want to know when he is actual dead. So this this is so this lump analysis is basically used. This is one of the application it is used to find out approximately when the person has died. So now before this, so how the lump analysis equation and how it is derived is T temperature at a time T minus the ambient temperature, but at the start the temperature. So this ratio is related to your the exponential of HA by rho CB. Now what is H? H is heat transfer coefficient of the fluid or the ambient air. A is the surface area. Rho is your density. C is specific heat. V is volume. Now before this we need to, because for this to be valid, for lumped analysis to be valid, Biot number has to be less than 0.1. This is the condition. Now first bit he has asked what is Biot number. So Biot number is again given as HLC by K, where LC is your volume by area. So volume by surface area. Now volume, he has asked us to model the body as a cylindrical, so volume will be pi r square L, and total surface area for cylinder will be this and the lateral area. So the cross section area is 2 pi r square, and there are two times bottom and top, and the lateral area is pi r L. So this is your characteristic length. So let's find out the value of this, because from then only we can find out the Biot number. Okay, so if I substitute the value which is given as radius is the 30 centimeter diameter, so 0.15, dia is 30 centimeter, length is 1.7 meters, so you have to just convert it here. So radius is 15 centimeters, so I'm just writing in terms of meters, so 0.15 by 2 pi r is again 0.15 whole square plus pi R into L, which is 1.7. So if I do all this, the characteristic length which I get is 0.0689 centimeter. So this is characteristic. So the Biot number would be HLC by K. H is given the heat transfer coefficient between air and the human body. That is given as 8 watt per meter square degree Celsius. H length, the characteristic length LC. So this is basically the non-dimensional number occurring in lumped analysis, and we are asked to find out. And the value of K is 0.617. So all that when I substitute, I get a Biot number 0.89. Now this is a higher value. So the first bit is 0.89. Answer option is C. Now what is asked is, so obviously going by the theory, this will not be a case of lumped analysis because Biot number has to be less than 0.1. The lower the Biot number, the better is your lumped model analysis approximation, because Biot number is low, that means thermal conductivity is very high. Thermal conductivity is very high, that means the spatial gradient of the temperature inside the solid body, here it is human body, so that is negligible. Okay, basically the thermal resistance is very low, the thermal conductivity resistance is very low. So now we are assumed that lumped analysis is there. So we are supposed to assume that and just estimate the percent death. So we'll just use this equation, and so temperature at a time which is at 5 p.m. it is 25, ambient temperature is 20, initial at the start of the process it's 37 minus 20. So this is how a body uniform temperature 37 starts losing heat and becomes 25. So throughout the body the temperature is 37, throughout the body at 5 p.m. the temperature is 25. Now we are asked to find when was this happening, when the body temperature was 37, because that is the time when all the metabolism, everything activity has stopped and it has started losing heat. So E minus, now HA. Okay, so how do I get this? HA by rho Cv. Okay, so let's find out this. HA by rho Cv. Okay, so this value H, so let me substitute. H is given as 8, length is area of array, and we need to just substitute this area. Okay, so let me write, so this is actually HA by rho Cv into time, T is there. So let me write this HA as B, HA by rho Cv as B, and let's calculate B separately, because otherwise everything at one place it will avoid problem. Okay, so when I substitute this, H is your 8, AS is your this entire surface area, so 2 pi 0.15 whole square plus pi into R into L by your density, which is, okay, now density I need to look at the figure. Density is given as 996 kg per meter cube. Specific heat 4.178 kilojoules, so 10 power 3, and so V, now volume again it's pi r square L, so pi into pi r square into L, so this is the total thing. So this, when you substitute everything, so remember that in this H is heat transfer coefficient, A is surface area, V is volume, C is specific heat, rho is density. So all that when I just keep it, what I get when I calculate the B value, which I get is 2.79 into 10 power minus 5 per second. Okay, so this I need to substitute here. So in this expression, so when I substitute, what I get is 25 minus 20 is 5, 37 minus 20 is 17, e power minus 2.79 into 10 power minus 5 into t. Now apply log on both sides and get t, because that is what we need to find, time t. So t comes out to be 438,605 seconds, and that when I just divide by 3600 I get 12.2 hours. So it is 12.2 hours before 5 p.m. that the person has actually died, when the temperature was 37 and the temperature started decreasing because of the heat transfer taking place from the body of from the human body. So this is just an exact application of your lumped analysis, and just you need to know this formula because this comes from your derivation of a lumped analysis. Only point here is the Biot number, though it is greater than zero point 0.1, but still in the 51st bit we are asked to assume that and carry out the analysis. So option is C for both of the bit. Thank you.